here is my hand in 5, my sortings. I made this header file where I included a struct that is needed for the tree sort, prototypes for the function print, bubble sort, selection sort, insertion sort, pivot picking, quick sort, build tree, print tree, change array, and tree info. I will show you them later. Here I state what you need in them. You need an array of to an index, and for example here you need the array and you need 2 points, and here you need a value in order to run it. So yeah, you have my header file here, and here we have all the coding. It's called sortpack.h, so we include all the prototypes from over here. And this is my printing function. It will run through a for loop for the index 0 to 9, and then it will see out the array of index I, and then it will end. I use this print function in all of my other functions, my sortings. We have the bubble sort here, where we have a double for loop. The first is from 0 to 9, and the second is from 1 to 9. And here we see if it's the position of our t, the array of index 1, is smaller than the position of the array of index 0, then we change the positions, and that's sort of the bubble sort. And then we print out the array. Oh, I might as well show you the bubble sort. Menu here I made in my main. So we have the array that is required for the sortings. Then I include the IOStream and my header file. And then we have the array, and I have the menu I have over here. And then I made a switch case to check what answer we want. And here we call the bubble sort function to the array we fixed up there. So this array is used for the bubble sort over here. And so yeah, we put it in here. So now it knows all of these index, and it will run the function and print it. And for example, if we go over here and press B, we see all of the steps since we put it inside the for loop to print. So we print every step. As you can see, the bubble sort is slow because it's really long. So it will take 8, and it will see, or it will take 19, and it will see, is 19 smaller than 8, and it's not, and then it will take 7 and say is 7 smaller than 19, and it is, and they will switch position, and then we'll take 1 smaller than 19, and yes it is, and they will change position, and then yeah, it will go all the way up until we have 19 and the last position. Then we'll take the next one. It's this pairing this, and that's why we have the double for loop and stuff. The next thing is the selection sort. Here again we only need the array I showed you in the main, so we'll just in our switch case call for the selection sort to the array. And we have a for loop here where we want from 0 to 9, and then we set this min equals to the O. So we have min equals to 0 in the beginning, and then all the way up to 9. And then we have another for loop, so we have the double for loop where we see if p that is equal to O plus 1, that means that p is 1, and p go up to 9. And here we run the for loop to see if the position in the array to p is less than the position to min, that is O. So if the position of 1 is less than the position of 0, we set min equals to p. So instead of min equals to 0, it will now be min equals to p, and then we change the position, and then we print the array. Selection sort. Here we have all the steps of the selection sort. Here it's fixed. You can see it's fixed pretty early, so we don't really have to run the loops all the way. So that's the selection sort, and then we have the insertion sort. where we again only need the index of the arrays, and we will run a for loop where we put j into the I integer, and then we see if j is more than 0, and if the position of j minus 1, that would mean 0, of the array position index 0 is bigger than the array index 1. If we will of course change the position, and j would be minus by 1. So I will show you. Search and sort. It will also run all the way up from 0 to 1 to here 19, number 1, not 0. 19 is here to see if it's bigger than 7, which it is, and then 7 will see, oh, I'm smaller than you, and it will go over here. And then 19 sees, oh, 1, am I bigger than you? And yes, it is, and 1 is smaller than 8 and smaller than 7, so we'll move over here. And then, of course, it will just move on all the way until it is sorted. And then we print out the sorted array to show that we transformed the original array to the new sorted, as we did in bubble and in selection sort. Then we have a function called pivot picking we are going to use for the quick sort. And here it says the pivot to be in the position of the array to the index r. And over here we decided what r is. R is set to be the last index in the array, 9, and the point p is set to be 0. So we have that while p0 is less than r9, then we have to check if the position of p is the value is smaller than the pivot, which is the position in the array of r, and then we will plus p with plus plus if it is smaller. While it is smaller, it will be plus, and we will see if p is less than r, which it is, and then we will transform the position to the other position and plus plus, and then it will run over and over again. And then we have the while the position of this is more than the pivot, and since we can do that, it's because the new pivot is set to be r to p. We change the pivot all the time, and then we have r minus minus, since it's supposed to be less than the pivot. And meanwhile, we are going to make it less than the pivot. We are checking if the position is equal to the position of the array to p is equal to the position of r, and if it is, we will plus p with plus plus, because we can't do none. And then we will return the r. And here we have a quick sort, our main function, that tells us that if p is less than r, we will have this j to the pivot picking, and we will run the pivot picking to the position p and r and all of that, since we also have it up here. So actually this will run the pivot picking to make a quick sort on the pivot picking minus 1 for the r position, and the pivot picking plus 1 on the p. So r will go 9, 8, 7, and p will go 0, 1. Here we have the print function to the array. So for example, if I show you quick sort, which is called quick sort for a reason, it happens really quick. Or it takes 3 as a pivot, and it puts everything less than 3 on this side and everything above 3 on this side. And then it takes 2 and put everything here, everything on the 2 on one side and everything above on the other. And then it takes 3 and then it puts everything above and everything on the other. Then it takes 7 and put everything under 7 and everything above 7. Then it takes 8 and again nothing happens, and so it will just run the last ones through to see if any changes is needed, and it's not. So yeah, and then we have the new order of the array is to show that we transformed the original array. Then we have the struct of node in data, and then we have node left and node right, and these are needed for the binary tree function, which is long. Then we have a variable called new pos equals 0 that we are going to use to transform the original array into this new sorted array. And then we have our function for the build tree that we'll see here. If value given is less than the position pointing to the data, then it sees if the position pointing left is nothing or null, and if it will make a new node and it will give that position left pointing at the data equals the value, and then it would set the left position or the right position equals to null. If not, else it will build tree again. It will run the function again. It's recursive. We will run it to the position left and the value. So the node position will be the position left. And then we have if the value is not less than the data, we will run this. Else we will see if the position to the right equals null. And if it equals null, we'll make a new node, and we will give it the position the data equals value, and we will make the position right left null and the position right null. And then we'll, of course, if the position is not null, run the function to this position right as the new node, and then the value. So again, recursive. Then we have the print tree, which will of course print our tree, and we need the position, and we need the whole array with 10 index. And then we have that if the position pointing left is not null, then we have to print tree, run this function to the position left and to the array, and then we have to print out the data, and if the position right is not null, then we have to print tree to this. So we'll print out the whole array. And then we have to change array, where we again see if the position is not null, and if it's not null, then the function it's recursive, so it will run itself at the position left and the array, and then it will take the array new position. If that ++ equals the data, we set it equal to the data, and then we have if the position right is null, then we will again run the function to this position and then the array. And then we have the tree info, which will run everything, and this is also the function we will call in our main. Then we have a new node called root that points to left equals null, and it points to right equals null, and then we have it pointing to the data to this is the value. It is set to index 0, and then we have a for loop that will run from 1 to 9, where we run the functions build tree to the index of from 1 to 9, and then we have that's the value, and then we have the print tree, and the change array is outside the for loop since we only have to do it once. So to see all the steps of the tree sort, you'll see here it will take the first index, that is 8, and it will say 19. Is that null? It's set to null, so if you take 19, it will say it's smaller or less than 8, and it's bigger and less than 8, and it's bigger, and just put it here, and then we'll take 7, and yeah, like a free make branches. So we can see all the steps, and then we can see that we make the new order of the array equals to this. So this is my hand in 5,